This is section 6.1, day 2. And first thing we're going to look at is how we can look at a slope field here and pick out the equation. So this slope field here, anytime you look at a slope field, there are some pretty significant characteristics you should look for. For instance, we see something here that might be really helpful. All of these lines have a slope of 0. So that's something to key into. So if we look at this, if we look at some characteristics to identify the slope field, that's the first thing we're going to look at, is where's the slope 0? And the slope is 0 all along here. Notice it's 0, it's 0, 0. And so when I say slope, you know, hopefully you're thinking derivative. So if we have 0 slope here, that means all of these values, dy, dx, are 0. And so if we look at that, we can think of this location relative to the origin as over 1, up 1. So at 1, 1, we have a slope of 0. So the question is if I put 1 here and 1 here, do I get 0? If I put 1 here and 1 here, do I get 0? And if I put 1 here and 1 here, do I get 0? And I do get 0 for a and b. So we're looking at setting that derivative equal to 0. Look for horizontal slope field lines. There they are. And so parts A and parts B are where if the slope is 0, then these two values are the same. And they make 0 when you subtract them, which is why I'm saying it's along the line y equals x. So and this is another way we can do this. We can set the differential equation equal to 0 and solve this. So when we do that, if we set this equal to 0, we get x equals y. We set this equal to 0, we get x equals y again. And that's where these 0 slope fields occur. And when we set that equal to 0, we don't. So we eliminate choice C. So that's the first thing to look for. So we know we've narrowed it down to A and B now. And so we start to look at, you know, these two choices, and we go back to the slope field and we can look at some other characteristics. So the next characteristic we're going to look at is where's the slope undefined? Undefined is a vertical line, and I don't really see any vertical lines. Maybe here, that's vertical, but it's only one single line. You know, it's not a whole pattern of lines. So I would say that for this particular slope field, we don't have this situation at all. We know that a vertical slope line is an undefined slope or an infinite slope. We don't have any on this one. So it's something to consider, but it's something we don't have in this example. So we don't need to really worry about looking at any of those. So how about where the slope is equal to 1? That's also something we can pick out pretty easily. So a slope of 1 looks like here, where it kind of looks like over 1, up 1. So here, along here, there's a slope of 1. And so that all that we're saying is that then dy dx equals 1. So you can picture a 1 here, a 1 here, and a 1 here. And so if we think about that, then if we look at where the slope fields are 1, these slope fields cross the y-axis here, and that's what this is saying here. It's going through the y-intercept equals 1. Okay, so as we're looking at then this line here has, if we draw a line along those slope lines, this line has the equation of y equals x plus 1. Y-intercept 1, slope of 1. So if we can set the slope equal to 1 here, and solve each of these for y, and if it matches this, then we know that's the equation that fits the slope field. So we take the first one, set it equal to 1, solve this for y, and we get, when we solve this for y, we bring y over here, we bring 1 over here, we get this. That's not that equation. So we know it's not A. We already know it's not C. So it's got, the right answer's got to be B. So let's take a look at what happens when we solve this. Set this equal to 1. So that's what we did here. And we solve this for y, bring the x to the other side, we get y equals x plus 1. That matches this equation. So we know it has to be B. We already know from the previous example that it's not C. So we definitely know the answer is B. But before we kind of leave this example, the last thing we want to look at, so we had a slope of 0, a slope undefined, a slope of 1. The other thing, we know it's got to be b, but the last thing we could look at is where's the slope negative 1, and that happens right here. And I'm not going to go into too much detail, so I'm going to click through this pretty quickly since we already know what the answer is. But we can go through the same rationale as we did here with slope of 1 and seeing that it has an intercept of negative 1 here. But, and that's what this is saying here. But we don't really need to consider any of this. It's just going to show us again that B is the right answer. So those are the 4 things to consider when picking out a slope field and matching it with a differential equation. Just a quick review here. Do you remember the derivative of e to the x? If you said e to the x, you are right. So that being the case, what do you think about reversing that process? How about the antiderivative of e to the x? In other words, can you move that way through this relationship? So the antiderivative of e to the x must also be e to the x. Remember, when we take antiderivatives and we have no lower and upper bound, we put on a constant of integration. Okay, and that constant of integration represents then a family of functions whose derivative is e to the x. How about this one? Do you remember what the derivative of the natural log of x is? Okay, remember both e to the x and natural log of x we discovered using the n-deriv function in our calculators. So do you remember that it's 1 over x? Remember doing n-deriv of 2 and getting 1/2, n-deriv of 3, natural log of 3 and getting 1/3. We went through that exploration last fall. So that being the case, then let's work through this relationship backwards. The antiderivative of 1 over x must be natural log of x and plus c. And we also introduced the absolute value here because we know we can't take the natural log of a negative number, right? If we think about the natural log function, all of that is in the first and the fourth quadrant. There are no negative values of x. So those are 2 things that we kind of put those things in the category of things we just need to remember in terms of being able to take antiderivatives. Okay, just a quick comment. We cannot integrate natural log of x, at least not yet. So for right now, that's a process that doesn't exist. It's actually a different course that we cover that in, but not this course. So if we talk about anti-differentiation, we have a lot of properties here, just like we had properties for differentiation. And if you notice, here's the differentiation properties. If we run them backwards, we get the anti-differentiation properties. So I'm not going to spend too much time on these, but that first one is your power rule, reversing the power rule. The second one is the natural log, and the third one is our exponential. And then we get into our trig functions here, and we'll talk more about those trig functions in this chapter, but we're just not going to spend a ton of time on them today. So we know that when we evaluate integrals, and those integrals are polynomials, that we use that power rule. So that being the case, let's try to do the antiderivative of this polynomial here, 2x squared minus 2x plus 5. So we know this is a polynomial, it's an expression, x to a power, so we're going to increase the power by 1, divide by the new power, and we're going to keep doing that for each term, and then when we're done, we're going to put a plus c on the end so that we can represent that family of functions whose derivative is this. So let's start with that first term, 2x squared, bump up the power and divide by the new power, and we'll just leave it like this. We'll simplify in the next step. Let's go to this next one. So minus 2, and then again, bump up x, the power on x to x squared, and divide by that new power 2. And again, we'll simplify in the next step. We won't worry about that right now. And then the antiderivative plus 5 is 5. And I really got carried away here with the power rule. This is 5x to the 0 power here before we took the antiderivative. So we're going to bump up the power rule to 1 and divide by 1. So now we can simplify this. So this we can write as 2/3 x cubed. This we can cancel the 2's, so we just have minus x squared, and this we really can simplify to 5x. And then we put our plus c in the end, and that's the antiderivative for this right here. So this plus c, it could be any number. We could have plus 2, and then when we took the derivative of this, we'd get this back. We could have minus 10, and when we take the derivative of this, we'd get this back again. So that plus c enables this whole thing to be a family of functions whose derivative is what we started with here. Let's try this one. So the antiderivative of 1 over the square root of x. Now, roots are always a little tricky, and so I like to think of roots as fractional powers because then I can use what I know with my power rule. So I'm going to rewrite this as x to the minus 1/2. Remember, the negative power comes from the fact that this is in the denominator. And now that I have this written as a power, I can go ahead and use my power rule. I bump this up by 1, so I add 1 and I get positive 1/2. And then I divide by that new power. So the antiderivative looks like this. X to the positive 1/2 divided by positive 1/2. And then I'm going to simplify this. Dividing by positive 1/2 is the same as multiplying by its reciprocal, 2. So this is really 2x to the 1/2 plus c. Again, there's that family of functions. We can also write x to the 1/2 power as root x. So we could also express this as 2 root x plus c. But this is probably the way we'll see it if we were asked this as a multiple choice question. Let's take a look at this expression. And this is a little different look, but really I'm asking you to do the same thing. The derivative is 5x to the minus 4th. I want you to find the antiderivative. So really what I'm asking you to do is re-express it so that the dx is over here and integrate it. So recognize that we have a negative power, and when we bump that up, we get one number to the right of negative 4. So as we differentiate, we got 5, and then x to the 1 power more is negative 3, and we divide by that new power, negative 3. And then we can rearrange this to simplify it a little bit. So this is negative 5/3 x to the minus 3. We put our plus c on the end so that we can represent the family of functions. And we can actually even put that x to the minus 3 back in the denominator and make it a positive power. And again, this last step here is probably how you would see that on a multiple choice test. Let's find the antiderivative for this. So again, it's here, this is the derivative. We want to find that function that has this as a derivative. And so it's the same question we've been working on all hour here. We're going to take the dx, put it over on the other side. I put brackets around this because it's 2 separate terms, just like we started out with the polynomial that had brackets around it too. And I want to do the antiderivative. So we have to recognize our trig rules here. We have to realize that we have to work backwards to find the antiderivative of cosine and sine. So when we're looking at this, we take this term by term. We can factor the 3 out. Cosine, the antiderivative of that is sine. And then plus 2, factor the 2 out, and the antiderivative of sine is negative cosine. And then I'm going to simplify this and put the minus sign between the 2 terms. And I'm going to put my plus c on the end. So here's the family of functions whose derivative is this. And I don't think that requires any simplifying. So at this point you should be ready to try some antidifferentiation on your day 2 homework. And ignore this. This is a typo. I haven't given you this yet. But at this point, if you want to do the proficiency quiz in Blackboard, you could also do that as well.